You've been studying the fundamental theorem of calculus, and in this video we're going to extend that thinking just a little bit and help you to think about what we're going to call the integral function. So far, I hope you've seen that the integral, the fundamental theorem of calculus, and the integral is designed to accumulate things. And specifically, we've been accumulating the area under a curve. But we can accumulate other things as well, as you'll see in this class. But for now, we've been accumulating area under the curve by thinking about infinitely many rectangles, infinitesimally thin, so that as we accumulate that area under the curve, we're not having any overlaps or gaps. But what I'd like you to do in this video, after we recap that just briefly, is to think about what we're going to call the integral function. So first of all, here it is. You've seen that if you were thinking about a situation where we had a velocity function, and if we were to sum up, that is, accumulate the area, so the height of those rectangles is represented by v of t, times the width of those rectangles is represented by delta t, dt, that area accumulated between a and b would give you the area under the curve. And in the previous videos, you've seen that also can be represented by this total change principle. That is, if you also could find the position, remember this was velocity, if you could find the position at the endpoint B, find the position at the endpoint A, and subtract them, you'll get the change in position. So both of those things turned out to have the same result. Now, the important thing here I want you to focus on is the relationship between this function and this function. If you're given a velocity function and we want to accumulate those areas of rectangles, that can likewise be accomplished or equivalently be accomplished by doing this total change of the position function. And we know from Calculus 1 that the relationship between velocity and position is that the derivative of position is velocity. So in general, we're thinking this is the rate of change, in this specific case, velocity. This is the position. So the derivative of this function produces this function. Now you're going to see in our textbook, and just in general, not just our textbook, but any textbook or any resource about calculus, that these relationships in the fundamental theorem of calculus can be represented in different ways. So for example, instead of using specifically velocity and position, because not everything in the world is velocity and position, we might use f prime of t here, and then the function f over here in our total change. But what's important is not the letters, but is the relationship between the quantities. This is a rate of change. This is the, like, backing up to the function that produced that rate of change. In fact, you've probably heard this called the antiderivative function. F is the antiderivative function. So like back here, if we took the derivative of s, we would get v. Now, if we took the derivative of f, you're going to get f prime. So obvious statement here, f prime of t is equal to f prime of t. Now there's another way that has been conventionally done in calculus to represent these quantities, and that is with lowercase and uppercase. So sometimes you'll see it this way. Lowercase f of t here, uppercase f here. The idea being, though, still that this is, your brain is thinking, this is a rate of change function, and then this is the function that would produce that rate of change, like velocity and position. But just generically speaking, the derivative of this function produces this function. Therefore, when we think this way, when we think kind of left to right, we're doing antiderivative. When you think right to left, the derivative of f produces f. That's what we're saying here. The derivative of capital F produces lowercase f. So you're going to see all of these as you progress through the exercises, or just in any calculus course, you're going to see this representation. Please right now just pause and make your brain realize that the point is this. The integrand, as we call it, is often generically you're thinking of a rate of change, and the result is a function f such that the derivative over here produces this function over here. Thus, it's called the antiderivative. And you see that noted right here. All right, so now, one more thing before we move on. What if we flip around the limits of integration? Like notice back here, I was integrating from a to b. And so we said find that antiderivative function, like the position function at the end point, and subtract the position or the antiderivative function at the beginning point. But what if we flip around those limits of integration? Then instead of f of b minus f of a, we would get f of a minus f of b. So my question to you is, and we will pause here, but what is the relationship? What happens if you evaluate a function at a first, subtract, evaluate the function at b second, versus evaluate at b first minus evaluate at a second? Well, the issue is that if you have b to a versus a to b, you'll get the same number. I mean, if you have two quantities that you're subtracting, and you subtract them in a different order, you get the same number, just opposite in sign. Think about it in just a real situation like 4 minus 2. 4 minus 2 is 2. Flip it around. 2 minus 4 is negative 2. Same number, but opposite sign when you subtract in the opposite order. So that's going to be important as we think about our integral functions here later. But when we reverse the order of integration, we're going to get the same result, but opposite in sign. Okay, so now what I'd like you to do is imagine a function. We're going to call that function g of x for just generic purposes here. G of x is a function that inputs x and outputs a quantity that is actually the integral of f of t dt. It is the accumulated area underneath f of t dt. Pause in there for a minute. I want you to just wrap your brain around what I'm saying here. We have a function, g of x, whose job is to keep track of the accumulated area from the end point 1 on the horizontal, or in this case the t-axis. We're going to accumulate area from 1 to whatever you want as an input, x. And that output will be g of x. So, for example, suppose you wanted to do the integral from 1 to 1. That is, if you input a 1 for x, then we would accumulate area from 1 to 1 under the curve f of t dt. Now, just for the sake of discussion, let's have an actual function to work with here. Here's one. I just made this up. Crazy function. All these little piecewise linear segments just for the sake of our discussion here. And so x equals 1 would be right here. So imagine we're going to accumulate, g of x is going to accumulate the area under the curve between 1 and whatever input you pick. I'm picking 1. So imagine accumulating area between 1 and 1. There's no area accumulated yet. So what we would say is that g of 1 is equal to 0. If you input a value of 1 for x into this function, you're going to output a 0 in this case. So when x equals 1, the output should be 0. We'll see that in a little bit. How about this? What if I input a 0 for x? Imagine accumulating area from 1 to 0. Now, for a moment, let's think of it the other way around. We usually look across left to right. If we were to accumulate area from 0 to 1, imagine just little bit by little bit. A little bit of area, a little bit more, 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 a little bit more. Imagine accumulating area, and we finally get to 1. We would have accumulated an area equivalent to the area of this triangle right here. But as you just saw previously, if instead we go 1 back to 0, instead of 0 to 1, whatever area we would have accumulated here would be the same number, but opposite in sign. So g of 0, in this case, is going to produce a negative however much area is accumulated in the area of this triangle right here. Now we could certainly find the area of that triangle right there. In fact, let's just do it. 1 by 1, and then it's half of that for the triangle, so the area would be a half. So this integral, or the output of this function, would be a half, but negative a half since we're accumulating it in the opposite direction. So when we input a 0, we're going to output a negative half. When we input a 1, we're going to output a 0. All right, let's keep going. What about 1 to 3? Imagine accumulating area from 1 to 3. So we're going to accumulate area from 1. Accumulate area, we have this little triangular piece here. And then look over here. When we talk about the area, we're talking about the area between the function and the horizontal axis. This area right in here. So the area we're accumulating would be some positive area here. And then here's what we do. When the area is located on the negative side of this vertical axis, we call that area negative. Now don't go weird on me here and think, well, what the heck is negative area? Like a black hole or what? No, the negative just designates a direction. Positive means the area is located on the positive side of the vertical axis. Negative area just means that that area is located on the negative side of the horizontal axis. And so we would accumulate some positive area, accumulate some negative area, and I think you can see that right around 2. The amount of area that's on the negative side and the amount of area that's on the positive side would be the same amount of area, but opposite sign, and so they would negate, and the integral would output a 0. And then accumulate all this area on the negative side, thus we would call that negative area. Now, in the next video, I'm going to ask you to sketch a graph of what this function g of x would look like. But we'll do that in the next video.